Final project is Classify Me If You Can. So where we evaluated the performance of existing models on Doodles recognition. Since Tim is currently on the plane, this presentation will be done by Ningzhi and me.
Okay, so doodle recognition can be hard for humans, let alone computers. So take a look at the 9 graphs on the right. So can't really tell that they are actually Eiffel Towers without the text prompt. So, so it's quite interesting to investigate how well some of the state-of-the-art computer vision models will do on the Doodle dataset. And specifically, we asked, what categories are they better at classifying? Are there common traits to categories that they do well or badly on? And what prompting gives the best result?
Our project may seem like a silly idea that came out of nowhere, but there have been real applications centered on Doodles recognition. Recently, there is some growing interest in using Doodles or sketches as a means of image retrieval or classification. A work proposed a practical method for zero-shot sketch-based image retrieval, where human sketches are used as queries to conduct retrieval of real photos from a database. Another work focused on the class incremental learning of object categories using sketches. Essentially, their framework allows the users to freely sketch a few examples of a novel class for the model to learn to recognize photos of that class. Doodles can also be used to assist in searching for a particular screen in a mobile app quickly. Another work proposed a way for users to draw quick sketches to help find a particular place they're trying to get to in the mobile app. This work is based on a machine learning model trained to extract visual features from mobile app screens. Then this trained model will extract visual features from a sketch drawn by the user and compare it with pre-computed visual features in the database, and eventually highlight the matching screen. A lot of these works rely on models to extract visual features from Doodles or categorize them, but as far as we know, not much work has been done to examine the effectiveness of pre-trained models such as CLIP on such tasks. Thus, we hope to examine the classification accuracy of these models and investigate the possible incorporation of these models in Doodle-related work in future settings.
So in our experiments, we mainly use the quick draw dataset created by Google. So the dataset mainly consists of the doodle images drawn purely by humans. And we selected 100 categories and 200, 100 images from each category for training and another 100 for testing. And for the models, we selected 2 advanced models, CLIP and ResNet-50. So both models have shown superb capability in image classification. So CLIP, given an image, the CLIP could then, using pure natural language, give the best text snippet corresponding to the image. And the ResNet-50 has also been trained on 1,000 categories of objects. So we fine-tuned both CLIP and ResNet-50. And for CLIP in particular, we also investigate its zero-shot classification and prompt engineering on the raw model.
The first experiment we ran was the zero-shot classification with CLIP. So we ran CLIP over images from 100 different categories, and we calculated both the top 1 and top 5 accuracies, as shown in this bar plot. It turned out that CLIP did a mediocre job in classifying doodle images, with the top 1 accuracy of 27.9% and the top 5 accuracy of 51.5%. However, it is to be noted that this accuracy is averaged over a wide range of values. For the categories that CLIP was good at recognizing, it predicted with nearly perfect scores. But for the categories that CLIP performed badly on, it got nothing right. So for example, the best categories for CLIP were line, smiley face, television, pants, and star. Some of the worst categories for CLIP to predict were pool, bottle cap, and garden hose, for which CLIP got nothing right. In particular, the most popular wrong guess for pool was flying saucer, the most popular wrong guess for bottle cap was hat, and the most popular wrong guess for garden hose was line.
So we summarize as follows. So for the categories that CLIP was good at, they tend to have their own quirks that distinguish them from other categories. So for example, the left two images are stars, which is characterized by the 5 points and the iconic geometric shape. However, for the categories that Clip was bad at, they're either too similar to another category, or too carelessly sketched or to be recognized, even by a human being. So the right two images belong to the category of camouflage, where the first image is just an abstract random drawing, and the second image more resembles a clothes rather than camouflage.
Specifically, we looked into the category garden hose as specifically we looked into the category garden hose. Um, Garden hose was falsely classified into four categories: line, paperclip, smiley face, and whale, because they were the most popular categories. And they're shown on the right. So by browsing through doodles from each of these wrong categories, we realized that many players represented the garden hose with a curvy line, hence clip predicted as line or paperclip or smiley face. Oh, my guess for the smiley face is that it has this long, iconic arc for the mouth. And also um, many users sketched the garden hose as spewing out water. And I guess that explains this association with the whale, which is also spewing water.
And since Clip allows users to customize their input prompt, it's natural to consider prompt engineering with Clip. So here in experiment 2, we tried three types of prompt input: an image of, a doodle of, and this is A, followed by the specific categories. And it turns out that the second input, a doodle of, achieves the highest accuracy in terms of both top 1 and top 5 accuracy. However, the difference is also marginal, with an increase of only 1% to 2%. So we see that it is quite difficult to correctly adapt Clip to another data set by solely prompt engineering.
The third experiment we ran was fine-tuning ResNet 50. So we trained the modified version of ResNet with 50 layers on the training set, and we ran the model to predict categories for the validation set after training. We show the result of the experiment side by side with the default clip, um, as is shown in this figure on the right. So we used an atom optimizer with default hyperparameters, a mini batch size of 8, and a learning rate of 0.001. We trained this model for 40 epochs using GPU provided by Google Colab. So taking a look at this bar plot, the top one accuracy improved by over 90%. It went up from 27.9% to 53.4%. And the top 5 accuracy also improved by over 60%. It went from 51.5% to 82.7%, which is pretty impressive, I would say.
And since prompt engineering isn't that satisfying, we then turn to solely fine-tune the model parameters of Clip. So we fine-tune Clip in a similar fashion to other models. So given a set of images and the corresponding text labels, the Clip model will then return the logits of both the images and the text. We then calculate the cross-entropy loss of both images and text between the logits and the ground truth. So our total loss is defined as the formula in the slide. So after just 5 epochs and a learning rate of 0.001, the fine-tune clip quickly achieves a satisfying result. So here in the plot, the fine-tune clip achieves a top 1 accuracy of almost 80% and the top 5 accuracy of 95%. It is worth noting that the top 1 accuracy of the fine-tune clip is almost as high as the top 5 accuracy of the fine-tune ResNet 50. It has also shown the robustness of clip, as it could be fine-tuned to any other data set within such a short training epoch.
So in conclusion, our study delved into the ability of existing models such as CLIP and ResNet to correctly identify doodle images. Through our investigation, we uncovered limitations in these models and propose potential causes of misclassification. In addition, our attempts at fine-tuning the model on the training dataset resulted in improvement performance on the validation set, as is shown by the bar plot in the left. In addition, we also tracked down the toughest 5 categories for clip in the beginning, which were pool, rainbow, garden hose, piano, and pond. But in the beginning, clip got nothing right for them. But after we fine-tuned ResNet 50, we were able to bring the accuracy for all these categories above 40%. And then after we fine-tuned clip, it did a pretty good job. At least it's able to tell the slight differences between the user sketch pond and the most similar looking flying saucer. So it can tell that it shows that Clip was actually learning something. It was a fun project to do. And finally, an important area for future research is to determine if such pre-trained models will lose their generalizability after being fine-tuned for the task of Doodles classification. And hence concludes our project. Thank you for listening.